Hey everybody, I'm gonna talk to you about pandas, not the animal, the Python library. We had some...
Can you hear upstairs? Good.
Someone is upstairs?
Yeah, there are people there.
Cool. So don't throw anything down on me. Just a quick question. Who here has ever worked with pandas in any capacity? Okay, so a lot of people will recognize when I make some sort of mistake. But the good news is that it is only like the introduction, the very basics. So like I assume that the bar is set very low. I'm gonna keep it simple and I will try to focus on the fundamentals. There is a lot of stuff that you can do in pandas, stuff that I'm not going to cover firstly.
Because it's, I dare to say, for specialists, people who employ some sort of specialized subset of that library for whatever reason they need to. And second of all, because personally, I am not using entirety of the library every single time I use it. I only use it very specific parts of it for my work or for my hobbies. So I wouldn't like to wade into any other territory since I do not want to embarrass myself more than I have to. So let's get started. And by the way, there's gonna be a demo at the end of the session. So it's broken, right? That's what we get for moving here. Okay, so I'm gonna start with the very basics. So some of you have already worked with pandas, so this will be very boring for you. By the way, there's a QR code anytime I'm dealing with something that you can find online, so you can just take a pic and read it later in a better manner than here. So right now pandas is on its version 1.5.1 and some change, and it's some sort of, you could almost say, premier tool when it comes to data processing in Python. True, there are other more specialized options, but pandas has become something of a go-to example when it comes to basically dealing with any sort of serializable tabular data for a variety of reasons. First of all, it's very, very, very modular. It's got very clear APIs that you can almost instantly recognize. When you have ever worked with Python, with arrays, with dictionaries, and standard data structures, pandas is intuitive to use. And second of all, it's lightweight. Installing it takes a handful of seconds, and we've lost the signal. Okay, takes a handful of seconds, and it has very few dependencies. It's one dependency that's absolutely vital is NumPy, because pandas is essentially, if you want to be exact, it's sort of an extension. Thanks to that, it has very good performance, arguably one of the best that's possible when it comes to processing this sort of data with an interpreted language. To be completely honest, most of that processing is not happening in Python, it's happening in compiled C, which is one of the reasons why, hypothetically speaking, you may encounter situations where your machine doesn't support it, but I haven't yet seen it happen in the wild. As long as you have a standard x86 or modern architecture, you should be fine. And for these reasons, pandas became one of the things that shows up in every single data science, machine learning, statistics, and related tutorial everywhere. And it's also a thing that found its way into many other applications beyond just showing people how good you are at something related to machine learning. I would like to emphasize just a few key aspects of it. So I'm gonna miss a lot, as I said, but I hope I'm gonna bring those areas into proper focus. The first things we need to talk about is data structures. Now, pandas, since it's data processing tool primarily, relies on them to do a bunch of the heavy lifting. And no data structure in pandas is more important than DataFrame. Now, I could talk a lot about how it's related to other data structures in terms of object-oriented paradigm. I'm not going to. Suffice to say that the tree is somewhat convoluted, but essentially, it behaves somewhat like a dictionary of NumPy arrays. If you have ever dealt with NumPy and with NumPy n-dimensional arrays, you know that it's a sort of a data structure that can hold almost arbitrary Python objects, but is most suited to holding and dealing with numerical values. Same goes essentially for DataFrame. However, thanks to various extensions, it can do just as well with strings, categorical data, date times, and other time-related data. You can adjust it in various ways to be more efficient, and you can perform various operations on it that you could never hope to do in pure NumPy. The basic way you access the DataFrame instance is just as you would access a dictionary, except that every key is essentially a column. Now, to those who have ever worked with some sort of relational database, you are very familiar with how the tables work and how they are dealt with. And I will get to that later. But I think that you will find it very nice that those kind of skills directly translate into how you can deal with data frames. If it helps, think about DataFrame as a relation in a database machine with somewhat specialized features and built-in analysis tools. Now, every single column is essentially an instance of a Sirius class, which, amusingly enough, Sirius is related to DataFrame. It's essentially a one-dimensional DataFrame. Although it has some noticeable differences, but for most part, you can use the same calls, you can use the same methods, you can rely on the same attributes, and it behaves almost in the same way. There are So moving on to the series itself. Now, the elements can be almost anything. You can put arbitrary objects, strings, numbers. You can, hypothetically speaking, store almost any sort of hashable objects, even in its index, which basically holds the addresses to individual elements. Although I would advise against toying with this too much, because if there's one thing you don't want to mess with, it's the primary keys in your database. Index essentially is an analogy to primary key column in your relational engine. So if you somehow manage to, shall we say, create a situation where it's not reliable, well, let's just say you might not find your data. Because of that, there's only one thing you can put there, and that's all the hashable data types. Now, once again, Sirius is essentially inheriting most of the aspects of DataFrame. So you can also treat it as a specialized dictionary. I don't know what's going on with the cable. Okay. But from the functional perspective, when you're working with it, you can always rely on it correctly broadcasting the operations you do with it. So things like comparisons, things like selections, additions, or whatever mathematical operations you want to deal with. There's also
operations you can perform, and everything will be automatically aligned so that you don't have to worry about manual alignment. This, by the way, can be a major headache. We have been a major headache, because if you think about it, if you want to add two different series together, or perform any operation with two series, how do you decide the elements that should go together? Well, Pandas takes care of that for you. If the index is in a proper way, formatted in a proper way, if it's the same index, it just works out. You don't have to sort anything, you don't have to think about it, and you don't have to manually check that it's done properly. Which is a big plus, because for the most part, when you're dealing with data, you have a lot of columns, and you have to do a lot of them, a lot of things with them to make them into something useful. The last thing you want to worry about is if you are actually dealing with the right values in the right place. You want to link that to something more efficient, something like the library. Now, thankfully, most of the pre-processing can be done in the moment you load the file from your drive. Now, Pandas has a lot of IO interfaces for basically all of the most common data file formats from CSV and TSV all the way to GF5. We can even load XML if it's properly formatted, and of course you can write most of them. There is slight difference between the writing and reading in as that Pandas does support reading from almost all of these formats without an issue, but writing is somewhat constrained for obvious reasons, mostly because, well, when you're dealing with multiple nested straight data structures, you can encounter somewhat, shall we say, ambiguous situations as to what's to come first. But there's a long debate in that and why it was working this way in Pandas documentation, and you can find out very quickly. I'm not gonna dwell on that. The point is that reading
writing files to your drive. So for example, when you want to access a remote database, because everything is a file in Unix Word world, you have a lot of options, up to and including basic preprocessing. Just one example. Suppose you get a CSV file, which actually doesn't have any commas in it, and instead for some reason uses dots. Now Pandas can just use a different separator. It's a single argument, you specify it, it works like charm. Or alternatively, suppose that for some reason the person that gave you the file has put the header on, not on the first row, but on the 50th row. Yeah, there is an argument for that. You can read header from any single row within the very first call you make, and out comes perfectly formatted data frame with addressable index and everything in the right place. And yes, you can also parse time data. There is certain amount of fiddling you have to do in some cases if the format of the timestamps isn't exactly, shall we say, up to spec. However, for the most part, simple conversion is enough, and you can then deal with it as you would with any other time value, which I will get to later, but it's fairly interesting. Now for the data manipulation, once you have the data actually loaded, Pandas offers a lot of the basic options right out of the box. Obviously it's not a specialized statistics library, but it can give you some basic measures, obviously the mean, the median, standard deviation, and so on. You can also process strings. So all of the basic string operations you know from Python, like turning case upside down, converting the case, putting everything in lowercase, or even splitting the strings and turning them into separate columns in the data frame. All of those things can happen. You can also perform a variety of binary operations. I was talking about the index alignment. You can use the index to align the data and then perform an operation that from two data frames or multiple series produces one series or one data frame. And obviously you can also apply any other function that can be applied to the whole series or data frame. Using the handy, using the apply method. Now the apply method accepts any callable, anything you can call. Most usually you will see that people are just putting basic lambdas in it because that's the quickest way to put something in there. But you can define any other callable. You can have your functions. You can have all the objects of arbitrary kind. The only thing that really matters is that it accepts the same dimension of data as you're putting in it. So, for example, if I'm applying this specific callable on an entire data frame, it is important that it can process every single column that's offered, and, not just one of them. Otherwise, we might end up with something we don't really want. Of course, you can supply additional arguments in that same apply call, arguments that will be put into the callable and applied to the processing of the entire series. But that's more of a specialized thing. It depends on what you actually need. I will get into that later. Now, data is nice, but it's not really useful unless you can actually get to it. And so when it comes to selecting, those who have ever worked with relational databases know that nothing is as powerful as conditionals. Of course, in Pandas, you can work with the same kinds of conditionals we could in relational databases. There is even a query method of the DataFrame and Sirius, which allows you to input a raw string, which has somewhat similar syntax to what you would see in SQL. However, it is much better to use more Python-esque syntax, where you make a conditional on the value of a specific series or multiple series compared to some sort of other, value or constant or variable. This way, you can produce a binary mask of the elements from within that original data structure, which is then used for retrieval of the specific values. Now, we're talking about everything from basic inequalities up to arbitrary complex, callables that retrieve, that return any true or false. So you can imagine the benefits this has when you're doing something with lots of data and you need to pre-process it or clean it up. You need to throw out some values, keep some others in, for example, based purely on not necessarily criteria knew beforehand, but criteria inferred from the data structure you were already processing. It's important to note that while, for the most part, data frames behave as they would if they were dictionaries, there are several slight caveats when it comes to accessing deeper levels of them. Sure, you can string the selectors, the square brackets, right after each other, but there's a problem when you want to assign values in this way. For those reasons, there's the log selectors, or to be specific, .log and .ilogs. Both of them are using the square bracket instead of the curly braces or anything else. That helps with recognizing what they're doing when you're reading the code. They are slightly specific in that this is not something that Python has out of the box. This is a Pandas construct, but for the most part they behave in the same way. You separate the the column and the row by comma, and you just you can slice as you would in normal lists. You can select multiple columns, multiple rows, single column, single row, whatever you want, whatever the combination, and you can assign in the same way. Once again, everything is aligned by index. So this way you can really easily comprehend what kind of data you're dealing with, even combine them if you want to. And that selection by mask and callable is actually also indexed. So hypothetically speaking, you can, if you were to, for example, create dummy columns. There's actually even a helper method that's just two dummies, which creates a bunch of dummy columns from a specific categorical variable. Now, just as in relational database, you have the group by operator, which can give you some really interesting statistics, once again, right out of the box. But it can also create a new data frame, which is actually what it does by default, but for the most part you're dealing with the outputs, which uses multi-index. Once you group something, you're actually changing the leveling of the index, so now you have multiple levels of it. This can be handy if you want to deal with multi-dimensional data, because sometimes you don't really care about every single individual, but you only want aggregates, and you don't want aggregates, just from the small groups, one from the large groups. Sometimes this is not sufficient, and you need to go even deeper. The thing about multi-indexes is that you can use them the same way as you would normal indexes, and you can later retrieve some portion of the data frame with multi-index and turn it into regular data frame with regular index later, if you want to. Now, accessing multi-indexes is as simple as with normal indexes. The only difference is that instead of a single value, you're using a tuple, either n tuple, depending on the levels of the index. Now, obviously, you can filter and you can call anything you want for the aggregates, but that goes for all of these operations. Pandas is relatively consistent. There are also some cases where you cannot expect 100% interoperability between the different constructs, but those are so specialized that I have barely encountered them. And obviously, when you finally have your data in the right form, cleaned up, and with some sort of aggregate statistics computed, you want to take a look at it. Now, thankfully, Pandas has a soft dependency on Matplotlib. You don't have to install it, by the way. You can keep it, away from your computer. But if you want nice graphs, Matplotlib can be installed, and with a single call, you can produce relatively decent graphics for histograms, box plots, and a bunch of other charts. And you can adjust various aspects of them to turn them into something you can immediately put on your website or in your work. Of course, you can also output HTML type visualizations in a table form sometimes. And yes, you can also retrieve some raw data about the data structures themselves, such as those calls you see there. We'll get to them if I get to do the demo. But suffice to say that all of these are very important if you want to deal with some optimizations and with basic recognition of the data you're dealing with, because they give you a bunch of statistics and info straight away in a single call. And by the way, they return data frames or the same data structure that you just called them on. So you can process them with the same tools as you would any other data frame, which is very helpful. Now, when it comes to that data manipulation, multi-indexing, as I've said, is one way you can really improve your performance. However, it's a more specialized approach. It relies on you actually wanting to access multi-dimensional data in the way they were intended to, or in the way they were gathered. Unfortunately, multi-dimensional isn't always the easiest thing to understand. Sometimes it's literally the opposite, and in those cases you have to rely on pivoting and operations that are adjacent to it to help you turn the data into something more manageable. Now, pivoting is the most general operator in this case. If you have ever pivoted a table in any table processor or anything similar, you know what it does. But for those who didn't, you can turn columns into rows, rows into values, columns into values, and so on. Basically, you can turn the table upside down and inside out. This can generate new insights. Once again, you can generate a bunch of aggregate statistics and measures from these new objects. And for the more, shall we say, specialized use cases, you get the unstack, stack, and melt. Melt especially is one of those interesting things because it does what you almost always don't want, but it's surprisingly useful because what it does is that it turns the dimensionality to as close as 1 as possible. And instead of having multiple columns, you end up with 2 columns, one describing the variable and one describing the measurement. Once again, most of the time, this is extremely unwieldy. But in many cases, this is one of those few things you can, for example, display on some output, and you can send over some sort of line. So it can get useful in one of those special cases when you need it. And when it comes to processing the data and manipulating it, not always you deal with straight table data. Sometimes you're dealing with time series, and in those cases, you can really use rolling. It's also called windowing. Those who have ever done any sort of aggregate statistics on time series data know what I'm talking about. But essentially, it's a time-based form of group by. You select a small segment of the data based on either index or on the timestamp. And you apply some sort of operator to it, producing one value or several values, but always fewer than those that you started with. There are various ways you can configure the window size and also the window shape. we can weight the window. So for example, values that are closer to the center have lower weights or higher weights. And of course, we can apply arbitrary operations to them. So technically speaking, you can have very complex operations performed on time series just with this one call. Of course, it depends on what you want. In most cases, you probably want to leave at least part of this work to more specialized libraries. For example, if you are dealing with modeling of time series, this is something that Scikit would do for you, or that you would, for example, just feed into your specialized software. But you can do this in Pandas and pre-process that for a fraction of cost and deliver it as a new file to your specialized model already. So that's a great benefit right there. And when we're talking about delivering the processed data, the important part is optimization. There's actually an entire chapter of it in the Pandas guide, where you can read a whole lot. But essentially, since everything is loaded in memory, and memory is a relatively constrained resource compared to storage, you might end up in a situation where you want to, not use all that much of it. Pandas is your back. You can, for example, that's the very basic thing. If you are dealing with strings that are essentially categorical in nature, you can turn it into specialized kind of series and basically have a categorical column, which instead of having a bunch of strings, essentially maps everything to digits, well, integers, and then you just displace the strings when you want it. You can also pivot it, as I've already mentioned, and melt it if you need to. This reduces the dimensionality substantially, and of course you can grab duplicates and empty rows and so on. But one more thing you can do, you can arbitrarily change the data types into something that's more useful for you. Yes, you might lose some resolution. Sometimes, however, it doesn't matter if you have float or a double. 32 bits is sometimes really all you need. And if it means that you halve your memory footprint and you're already dealing with more than gigabytes data, it's well worth it. Same goes obviously to all the other ways you can handle your numerical values. And the compatibility with NumPy extends to this. So any single NumPy data type is usable within Pandas. That includes the resolution, and of course it means that you can apply the same calls as you would in NumPy. I think there are a handful of caveats where you might have to be careful about the specialized use cases, but I haven't encountered them in the wild, and definitely not in my own work. That being said, you should obviously be careful about increasing the resolution, because 64 bits takes up twice as much space as 32. So you can end up with something that doesn't fit into your memory very quickly, and well, you don't want that for obvious reasons. I'm gonna head to demo right now, and we'll see if it works slightly better than.
So maybe we can have half a minute to play.
Okay, sure. I'm just gonna move to the command line. so we're, fine. Just give me a shout when everybody can see what I'm typing, right? Is that enough? Can everybody see?
Yeah.
Okay. So for the demo, which is gonna be I'm gonna be honest, very basic. I picked a very small and venerable data set. Has anybody ever heard about the Iris data set? Ever? Yeah, it's one of those that you always see in textbooks. It's just got 150 values, and yeah, it's basically just measurements of flowers, petals, and sepals, and there's always the name of the species. I'm gonna show you some basic operations on it with Pandas. I just hope it's gonna work out, because it would be very embarrassing if I messed up now. I've loaded the environment with just Pandas, and it's one dependency, which is NumPy, and everything else is just what you see there, what you get every single modern Python, basically, unless you really want to get rid of it. Just to show you what we have here, and I've got it in Iris CSV. So this is what we're going to be working with. We got 4 numerical columns and 1 string column. I'm going to keep the same nomenclature as they do in most of those tutorials and documentation you find online. So if you feel like you're experiencing some déjà vu, it's because of that. It's not because there's a break in matrix or something. So first of all, we're gonna load our data frame. You can see right away that we have a bunch of those options I was talking about for I/O access to various data sources. In our case, CSV is obviously what we want. We can just type in the path. And here we go. So you might notice something's wrong there right away. What was it? Yeah. So the columns are messed up in the description. And the reason why is because our data source, specifically a certain American university I will give you a link to after at the end of the presentation, didn't include any header in that data file at all. It just, started with the first value. Just fine, but obviously Pandas can just guess. So we'll have to do that over. And this time we'll have to apply the header name, the header ourselves. We can just have a list. And by memory, I believe the first one is sepal length. And then we have sepal width. And followed by petal length, and petal, width. And finally we've got the species of our iris flower. Okay, we have the right names of our columns. Notice the first column is the index. The curtain almost covers it, but not completely. I can move it a bit. No, I'm not going to. It's better this way. But the first column is the index. In our case, thank you very much. It's numerical, so it's the easiest thing to work with. And you can see that we have the 150 values there. By the way, 2 of those rows are wrong according to the data source. I don't know which ones those are, but I'm going to demonstrate on 2 randomly or semi-randomly selected rows how to, pick up something you're interested in. Now, for the most part, if you want a single column, you can access it in 2 ways. You can either try the dictionary route, or you can try to access it with dot notation. because Pandas automatically creates those attributes for you, and you can this way access them in a much easier way. You also benefit from the obvious, recommendations for the tab completion, which is very useful when you're using something like Jupyter Notebook and you're really trying to type something fast and you don't want to do a bunch of strings. This saves a lot of time in the long run, although it may seem that it doesn't. Also note the data type, it's float 64 or double. We don't really need that, and I'm gonna get to that later, but we can drop that to 32 obviously and keep the same resolution, because these are just, you just take one floating point value. Sorry.
And how about collisions with methods?
Hypothetically speaking, that can happen. It didn't happen to me yet, but we can try that. I mean, we can try that. I honestly haven't encountered that. So let's see what we get here. I'm gonna try. I'm gonna try the STD, because that seems like the most probable thing that someone could fill in, for example, for medical reasons. I'm gonna put something in there. Let's just put 0 in there. Try to broadcast it. So what happens now? I'm wondering when I try to tab complete for STD. Okay, so it's giving me method first. So it seems like Pandas is a bit smarter than that. Instead, it just gives me D. But the column is there. So if I want to know what kind of STDs these flowers have, I'm just gonna get it. It's a 0. I'm not gonna fill out what the 0 stands for, but imagine anything you want. Really, it's up to you. Like I wouldn't want to do that. But yes, Pandas is a bit smarter than letting you create a name collision, just because you want. Also note that the future warning right here, because we have called our standard deviation on something that's not exactly numeric, on the species column. We called it on our entire data frame, including that one column, which is definitely not numeric. It used to be that it didn't give those warnings. Now it does. I really would advise you to pay attention to them, lest you come to your project about half a year later, run it with a new version of Pandas, and suddenly realize that everything is broken. It's really not worth it. It saves a lot of time in the long run. Moving on to the selection of data, we can, for example, use the walk in the same way. Now, in our case, I'm going to try the STD again. And you can notice that I have got the key error, because technically speaking, I've messed up the order. So there comes the first error of my presentation, I hope. You can later tell me I made some others. But this way, you can select as well. It's slightly different. First of all, you notice this column here. It's very similar, it's almost the exact same syntax as you use in Python with slicing lists. So thanks to our very simple index, I can just get these 6 values, or I can pick an arbitrary range actually. And at the same time, I can try to do some basic masking and selection based on values. So in this case, I want to try something like select all sepal lengths, select all elements with sepal lengths that are less than some value. So I'm going to try something, it seems like, not that small, or maybe slightly small. Okay, like this. I'm using the same notation as I would if I was selecting from a dictionary. As if I was using a dictionary, the brackets. But note that I'm putting a selector in there. And you can put also the bracket notation, but the result will be largely the same. In this case, nothing came out. You might be wondering why. It's because there is no element that satisfies that condition. If I get sepal length and right? We'll see why. So the minimum is actually 4.3, so nothing really satisfies our condition. So if I just adjust the condition to be, oh, let's say 5, I'm already getting something. Now you can see why the dataset is so widely used, because really it's fairly apparent that species is somehow related to some of these values, apart from the STD, obviously. That seems almost universal. But you can do a whole lot of other stuff with this. As you've noticed, we got something out of this, some sort of output. So what that output is, it's a data frame on which you can perform all the same operations as you did before. And obviously, that data frame has the index which is compatible with that of the previous data frame. All of those values are unique, so hypothetically speaking, if I just picked out all the measurements that were wrong for some reason, and I had a new data source with the right measurements, all I would have to do is to just replace them in the new and put it back in the old. Or even better, I could just assign it straight away. Of course, I'd rather do that with a log, but the principle is the same. Now, in my case, I don't want to really, do that in every single place. So I'm not gonna. I think we can do that for the STE column. So suppose that all of those have some sort of different STD, and let's say the STD is 1. And suddenly we've got a bunch of those with STD number 1, which is something worse than 0. And of course, in the same way, we can adjust the other columns, but I'm not going to go into that. I think it's self-evident how we would do it. I'm going to get to group by, because that's also one of those interesting things that you will end up using a lot. In our case, it's fairly obvious that we don't have really much to group things by, because all those are numeric values except for 2 of them, which are basically categorical. And I'm going to use species to mix things up. And what we get from it is a group by object. Now, on that object, you can apply a variety of the methods I've shown you before, those producing aggregate measures and those working with multiple data points at the same time. For us, the easiest thing to apply is obviously something like mean, or something we have to do something. For example, mean. So we get a mean value for every single variable, for every single species. Once again, notice that this is also a data frame. And in this case, in case of this specific data frame, if you look at the index, you see different manner of index, not numerical one, and a named one, actually. Indexes can have error names, obviously. I didn't mention that, but it's one of those things that you will find useful when you're dealing with multiple data frames at the same time that are not compatible for some reason, and transforming them into various other things. Naming the index gives you some sort of not only control, but also way to actually assign different meanings to them without just resorting to hashes. So that can be very useful potentially. Of course, you can do other things with grouping, but I think you can already figure out what kind of stuff we're talking about. What I wanted to get into, though, is various aggregate measurements and various ways you can adjust the data with the apply. So I'm going to do the petal width this time. And we're going to try some sort of function of these. Sorry, that's 2 P's, right? Yeah, right. So we want something that's very simple, something that's not gonna mess things up, and I'm gonna just do slight, decrease of the value. As you note, it's applied immediately. It's extremely simple. The syntax couldn't be easier to understand. We can do something slightly more complex. We can try to make it callable. I'm gonna call it normalize maybe. And one of the first argument is gonna be the Sirius itself. Second argument is gonna be the standard deviation. Oh, that's unfortunate. Okay. Okay. I'm gonna go with something less loaded. I'm just gonna write deviate. I'm gonna write def and mean. And I'm gonna try something called min-max normalization. I'm wondering if I'm remembering it right, but I think it goes something like this. Oh yeah, I also, no, wait a minute, I forgot. No, this is wrong. This is wrong, I forgot about yeah, it's not mean, and it's not div, it's min and max. Okay, hence the min-max normalization, right? So, you get your series. In this case, it's a single point you're getting at that time. And what you want is to, this is one of those things that you sometimes use when it comes to processing data that's of numerical type. So you get max, minimum, and you subtract from the value the minimum. I hope I didn't mess up the variables. Okay, now we've got our callable, and we can try to apply it. And it's gonna be just rise, and I think the argument we want is args. And just wondering, getting this right. So it's gonna be petal width. Yeah, and I'm wondering if it's arcs or arguments. We will see. And here we get it. It's perfectly normalized. Within 0 to 1, right? And you can imagine what kind of callables you might think up. You don't have to obviously just apply things from the same series. You can apply any single value or argument you want. The ways you can adjust this are basically limitless. And I'm gonna go to one last thing. If you get some sort of questions, so you can ask them later, and that's the optimization. So like, if you take a look at this data frame with info, it gives you the runtime evaluation of what it actually is, including the types of the columns, and especially the memory footprint. Now in our case, it's minuscule, comparable to basically anything. But imagine if we didn't have 150, if we get 1,500,000 values, that would be way worse. And we're wasting a lot of space on this object column here, and also on all of these floats, and arguably on the int as well. So what we can do is to, well, not that. And we can try as type. And there are various things we can do with as type. We can try categorical, which, as you know, maps the, oh wait a minute, I messed it up. What's the name of it? You know what? I'm gonna do ASTD. I'm done with this. I'm not gonna waste time figuring out how I forgot that one specific argument. Well, the type, the data type. I'm gonna just cut to the chase and do the int. Oh yeah. Okay. And and if we just assign it, I think we can get away with unsafe assignment in this case. And previously we had like 7.4 kilobytes, right? So now we got 6.1, which is way better. Arguably we could save way more if we turn the object into something else, but I forgot the name of the data type. So I can show you that, but I can promise you that it will be at least 2 kilobytes less than what it is now. So yeah, after 2 at least embarrassments and 1 insult to the flowers, I'm completing my presentation. And before I go, I just want to show you a handful of links to related projects and to the data set I used. Now I don't remember which American university it was. I'm thinking maybe, I don't know, Michigan, maybe something like that. The point is they got a vast array of data sets for various benchmarking purposes, and Iris is one of them. It's one of those that's always popping up everywhere. After NIST, it's the most popular one today, even. And if you want to download it and play with it, this is the best source. They're also not above admitting their own mistakes, because they themselves are saying that they messed up 2 entries. On the other hand, it's over a century ago since it was published, so you know. NumPy itself, the one that this whole thing is based on, obviously. And finally, Cython. Now, those of you who have ever used Cython know why it's so great, and Pandas people know it too because they're using it too. Basically, it lets you to leverage, allows you to leverage some of the optimizations and some of the ways C is better performance-wise over Python, while writing Python with a couple of decorators. Yes, it also means you have to essentially compile stuff, so it's not possible to do this everywhere, unlike with interpreter. On the other hand, if you're dealing with something that's very I/O bound, or that you have to really, you know, squeeze every microsecond or nanosecond out of, Cython is for you. So try it out and try out Pandas, please. Thank you very much.
Very much. Now, given the time, we will do a little bit different question time, and that is that if you have questions, please pop by. Easy and ask questions. Probably, ideally, it will be also showcased in the terminal, so that's handy. Does anyone have lightning talk? Today? No, that's also very handy. Good. Yeah, so networking time, question time, and please remember that in 2 hours we have to evacuate this place. And next Python meetup is going to be the special December edition, which is hardware related. And again, we're not going to be either here or out there, but we're going to be probably in Jakarta, but we will specify that closer in all the possible places. Good. Join Discord, join fun, have some beer, enjoy, and ask questions.
It was category, not categorical.
And thank you for pushing through all the technical difficulties. That was great, and also thank you there for helping with opening the curtain. We are hiring